Hey friends, Ben again. This is a video for the differential equations class. We're looking at the notion of reduction of order. So the idea with this is that you have a higher order differential equation and you know one solution, and knowing that one solution lets you try something to try to make the equation easier. You know how if you're solving a polynomial equation, and you know one solution, then you can divide out a factor and it's a lower factor. This is kind of like that. Um, Naturally, there's a little bit more to it than that. Okay. But so the thing that we're going to do is to think about having, now, here, let me show you on screen. All right, so this, as I said, is the reduction of order technique. And the essential notion of it is that if you've got a solution, and we refer to it as y1, of some nth order linear homogeneous differential equation that you can express as L of d times the y is equal to 0, then when you substitute in y to be u times that y1. Now remember, y1 is not an unknown at this point. Y1 is a function, okay? So you substitute that in, and it's going to effectively make it a lower degree equation, because now all of the just u's will end up canceling out, and you'll be able to then try to solve for something that has u primes in it. And so you just let like v equal u prime, and v double prime, or v prime will be u double prime, and so forth. And so it makes it 1 degree lower. So then the question of why here. So if you take the derivative, of u times this y1, the product rule is going to have you doing that as u prime y1 plus u times y1 prime. Now, any term that doesn't have a derivative in it, the product rule doesn't apply to, right? But that means that when you apply your linear differential operator, your L of d to the uy1, there's going to be a bunch of stuff come out, but then there will also be stuff here that all matches up to have the L of d times y1, and that part's going to be equal to 0, okay? So as I say here, any of the terms that don't have a derivative of that with them are going to end up going into that u times L of d y1, as opposed to into the stuff section. I hope you enjoy my silly use of naming convention there. So what we're going to try to do is one that we know how to get the answer to. I always think it's best to do a problem you know the answer to, and then try to venture onto something you don't know the answer to. All right. So this one here says, given that y equals e to the 2t is a solution of y double prime minus 4y equals 0, find another linearly independent solution. Now you already know the answer, because you just go through there and say that's r squared minus 4 equals 0, and the r is going to be equal to plus or minus 2. So you know the answer, and we're going to just get it a different way. So what we do is we say y equals u times this e to the 2t, all right? Now we need to figure out what y double prime is. So on the way there, we'll do y prime. And then we'll do y double prime. And let's see, n plus 4u e to the 2t. Okay. So then our y double prime minus 4y is going to be u double prime e to the 2t plus 2u prime e to the 2t plus 4u e to the 2t. So far, this doesn't look like it's helped much. Minus 4 times u e to the 2t. Now we'll see why it helps, is that these terms have gone away. And remember, we want to set this stuff equal to 0. So you have u double prime plus 2u prime, then e to the 2t equals 0. Because e to the 2t cannot be 0, we can just cancel that out. And so now we have to solve u double prime plus 2u prime equals 0. For which you might say, dude, that didn't help a bit, right? But what it's going to do here, and hang on, let me check to make sure that guys, I need to apologize because I made a copying error. And I'm sure y'all caught this, and I just totally missed it as I was going along here. So when we were taking this second derivative here, okay, we had to do the product rule here. And of course, one of the terms is u prime e to the 2t. And then the other term of that ends up being plus 2u prime e to the 2t. But then when we do this, we got to do a product rule as well. And that's where I made my mistake. That should have turned out to be 4. Man, if I were a better liar, I would claim I did that on purpose. But the only reason I spotted it is because I worked it out ahead of time and I know what the answer is supposed to be. So, all right. So we get down to this portion here where we got our u double prime plus 4u prime is equal to 0. And as I said before, it seems like that didn't help because it's still a second order equation. But you could say, hey, I'm going to set v equal to u prime, which means v prime is u double prime, and this becomes v prime plus 4v equals 0. Now, if you'd like, if you don't have any problems just dealing with u prime as a symbol, you don't really have to do this, okay? But for me, it's helping us see that this turned into a first order linear equation. And so we can simply say my mu is going to be e to the integral of 4 dt. Well, that's e to the 4t, right? Let me check on that and make sure. Yeah. So I've got e to the 4t v prime plus e to the 4t v equals 0. And that is the same as saying e to the 4t v quantity prime equals 0. I integrate both sides, and I have an e to the 4t v over here because the integral and the derivative cancel out. And I have a constant over there. So the v that I'm getting then is c e to the minus 4t. And since v was really u prime, I can get u by integrating that. I have a minus 1/4 c. You could just take that minus 1/4 and make it into a different c. So that's not a big deal. E to the minus 4t plus, now I'm going to put a d on the end for my integration constant. So that means that the y I was originally looking for would be this u, which I'm going to write it as c e to the minus 4t plus d times that y1. What was that y1? E to the 2t, right? E to the 2t. So when I multiply here, c e to the minus 2t plus d e to the 2t. Anything that I choose any values of C and D, as long as they're not both zero, as long as I don't choose a zero in a bad way, then I end up with a linearly independent solution. So that's applying that that reduction of order technique there. Okay. All right, then let me hop over here to another example where we're doing we're doing the same thing, but now we're going to see the reason why we have to get a t in our second solution when we have, you know, the multiplicity 2 and stuff. And we're going to do it in general here. So any linear constant second order differential equation where you've got the d minus a being squared there would be expressed out into this form that you can see right here. Okay. Now, one solution you'll get comes from the r squared minus 2ra plus r squared. I wrote r squared, I meant a squared. A squared equals 0, r minus a squared there when you factor it. And that gets you r equals a with a multiplicity of 2. Okay, so so far we've gotten the one solution that we're used to, the y1 equals e to the at, all right? And instead of going ahead and writing down t e to the at for the other solution, we're going to show how that comes about. Because now we're going to say y equals u, with u unknown, e to the at, and we have to figure out the y prime and the y double prime. So we have to use a product rule here. We'll have u prime e to the at plus a u e to the at. And then that's going to give us the y double prime. And I got to be careful and not lose anything this time. Remember, I copied it wrong last time. U double prime e to the at plus, let's go ahead and I'll just write each term out if I need to. So that's from the first product rule. And then on the second product rule, I'll have an a u prime e to the at, and also an a squared u e to the at. So picking up that extra a there from that. So if I gathered it together, nope, I don't think I want to gather it together. If I wrote it out, u double prime e to the at plus 2a u e to the at plus a squared u e to the at. All right. Ugh. So what we're having to write, remember, is y double prime plus, no, what was it? Minus 2ay prime, and then plus a squared y. And we're going to set it all equal to 0 and stuff, but let's go ahead and just expand out here. And we'll have u double prime e to the at plus 2a u prime e to the at plus a squared u e to the at. And let's see, then what was it? Minus 2a times this one here. So minus 2a u prime e to the at and minus 2a squared u e to the at. And then finally plus a squared times this. So plus a squared u e to the at. And then we're going to set it equal to 0 after this. But first we see that this cancels out and this cancels out. So that means we've got u double prime e to the at, which we need to set equal to 0. Now, e to the at cannot be 0, so we can just divide by it and cancel it out. And we have u double prime equals 0. If you integrate that once, u prime has to be some c, If you integrate it again, the u has to be some ct plus d, okay? And then if you substitute back in, you've got the u, ct plus d, times e to the at. So you have ct e to the at plus d e to the at. That's the general solution. If you only need a second linearly independent solution, then you just pick c to be 1 and d to be 0. But if you want the general solution, then it's sitting there, okay? So, yay! So this reduction of order technique is actually the reason why we have that, that setup of what to do with the multiplicities. Now, if you are wise, that has you trembling in fear because you know what I'm about to pull is I'm going to say, hey, look, turns out that reduction of order technique doesn't have to be on constant coefficient stuff. And so we're going to see why we get the logarithm showing up on these equidimensional equations when you have the repeated roots, okay? But these are enough of a pain that we're actually going to do a particular example. So I hope that helps a little bit. So, all right, so we're going to use the reduction of order technique to solve this. And because it is an equidimensional equation, we're going to say, well, my y solution ought to be t to the r, y prime is r, t to the r minus 1, y double prime is r minus 1, t to the r minus 2. And then when I substitute those in over here, I will end up with an r minus 1, t to the r, minus an r, t to the r, and plus a t to the r, right? No, hang on, I wrote the wrong thing there. Plus a t to the r, like that. Okay. And if you go ahead and factor out, you'll have an r squared, and let's see, minus 2r and plus 1, and t to the r equals 0. Now, if t is not 0, we can go ahead and divide that out, and we have r minus 1 squared, which says r equals 1 with a multiplicity of 2. Okay? So we have a solution that's telling us our y1 is t to the 1. Okay? I'll just write that as t though. And now we're saying for our reduction of order that we're going to let our y be equal to ut. And so our y prime would be u prime t plus u. I started to say u times t prime, but derivative of t is just 1. And then our y double prime, we're going to have a u double prime t plus, and then a u prime times the derivative of t is 1 plus a u prime. And so we can simplify this as u double prime t plus 2 u prime. As a matter of fact, if you took more derivatives there, it would have kind of a neat property that it would just kind of it would kind of just throw down more of those one derivative downs. So your third derivative would have u triple prime t plus 3 u double prime. It's kind of neat. I might be a nerd. Okay. So the original equation, which I've already lost track of, was t squared y double prime, what was it? Minus ty prime, and then plus y equaling 0. But we're going to do all of our substitution as we go here, all right? So we got a t squared times the y double prime is u double prime t plus 2 u prime, and then minus t times the y prime was u prime t plus u, and then plus the y was just ut. We'll expand it out. And I'm going to write my t's before my u's. I guess that might look like I'm kind of being OCD or something, but yeah. If you've seen my office, you'll know that that is fake news to claim me of being OCD. So TU. See, did I get that right? STU. I feel like I copied that wrong, and I am totally gonna. I'm going to cheat and pause to check myself. Or I'm going to. Sorry about that. I forgot to copy that down, which means these two things cancel out. And then the other part doesn't quite. So plus t squared u prime. Now we're having to set this all equal to 0. Okay, so if you set your v to be u prime, then our v prime is just u, and we have t cubed v prime plus t squared v equals 0. We divide out, and we have v prime plus 1 over t v equals 0. We're going to have to do our integrating factor. That's e to the integral 1 over t dt, e to the ln t, which is just t. So we'll have t v prime plus v quantity prime equals 0 times t is just 0. And this prime does not belong there. It belongs here. And when we integrate, we'll have tv equals just some constant there. And then our v is going to be the c over t, but our v was really u prime. We just cleverly disguised it. So our u is going to be c log t plus some d, and our y, our general solution, once again, c log t plus d times t. So c, I'll write it as t log t plus dt. So the first solution was that t, the second solution was that t log t. So we could have done that in more general terms, but we're not really benefiting all that much from it. So really, your reduction of order technique, the biggest thing about it is that it justifies why we do the multiplicity, what we do with the multiplicity when we have terms that don't have multiplicity of 1 in the initial or characteristic equation. Now, it also turns out that that technique is going to allow us to do 1 or 2 other things, and it's also going to have a parallel that happens in the variation of parameters technique, which is our next thing to do. So go ahead and do these. It's bookkeeping. You have to keep a careful track of your algebra. Go ahead and do these, and then I'll get the video ready for doing variation of parameters. All right. Thanks a lot. I'll see you in class.